This is the screencast for section 4.6, example 7. We are going to express the sum of sinusoids as a sinusoid. So basically we're going to take the 2 or 3 pieces of a function of 2 or 3 sinusoids that we added or subtracted together from example 6, and we're going to make one sinusoid out of it. We are going to find the final horizontal stretch or shrink, horizontal shift, and vertical stretch for that sinusoid. So example 7 says let f of x equal this function. And then it also states that from the discussion above, which is example 6, you should conclude that f of x is a sinusoid. And we see that because the b value is the same for both. The period of f is directly related to that b value. So since b equals 1, the period is going to stay the same. Period is going to be 2 pi. Sines period and cosines period are both 2 pi. There is no horizontal stretch or shrink to change that otherwise, so we still have a period of 2 pi. In part B, it says estimate the amplitude and phase shift graphically to the nearest hundredth. So what I've done is I've found the maximum value of this sinusoid. I've graphed the sinusoid in my calculator and found the maximum value, which is 5.39. That is my amplitude. That is how far my sine curve, this sinusoid I'm trying to construct, has been stretched. So since the amplitude is 5.39, that means the a value is going to be 5.39. The amplitude of a normal sine curve is 1, but now we've stretched it by 5.39, a vertical stretch by 5.39. The second part says estimate the phase shift graphically. Well, a normal sine curve is going to cross through the origin as it is increasing. So I've got to find out where that point went. So here it is. I found this 0 using my calculator, and that is at negative 1.19. So this was a phase shift left 1.19. which means the h value is going to be negative 1.19. If you don't remember what our final goal is here, the formula for a sinusoid is down here. So the h value, the horizontal shift left or right, is right there. Now, to give a sinusoid, we want to give a sinusoid of this that approximates f of x, of this form that approximates f of x. Well, we've identified all the values we need to identify. F of x equals a comes from the amplitude 5.39 times the sine of b is going to be 1, so I don't really need to worry about that. X minus h, well, I'm subtracting negative 1.19. Horizontals are weird. So just to double check myself, I graphed my original function, the two sinusoids being summed together, and then I graphed the one that I developed in Y2, made it dark so I could see it graph over the top of the first one. So I did this correctly. The now try problem, example 29, is asking us to do the same process. So I graphed the original function, and I found the 0 that used to pass through the origin of a normal sine function, and that was at 0.49. So the h value is 0.49. There is a phase shift right 0.49. Now, the maximum value is going to be my amplitude, which is 3.61. So the amplitude, which means A. Let's see. Oh, and then let's not forget about our B value. Our B value had to be the same in the first place because this is a sinusoid. The B value is 2, which means this did have a horizontal shrink by 1/2, which is why the period is pi. Just in case you were curious, the period of this one is pi. So the b value equals 2. So my final sinusoid is going to be y equals the amplitude 3.61 times the sine of the b value times x minus the phase shift, 0.49, or the h value. So again, just to be sure, I graphed that in y2 against the original function in y1, made that dark, and I can see that it is graphing exactly over the original one. It is an estimate because in your calculator you got these decimals that went on forever. But as you can see, it is a pretty darn close estimate. So, and I believe the original example back here even asked for a sinusoid that approximates f of x. So your book does recognize that this is not exact, and you should recognize that too.